Okay, just an addendum on the preceding. I had 6s and 4s jumbled up in my head, and the bullet mass is 40 grams, which is 100 times the 100th of the 4 kilogram mass of the gun. Anyhow, so that's why the bullet ends up moving 100 times as fast as the gun. Okay, now, very quickly, we have a collision of a 100 kilogram football player diving for the end zone and a 90 kilogram defender diving for the runner. And they collide in midair. The runner is moving at 8 meters per second, the defender at 6 meters per second in the perpendicular direction. So what's their velocity going to be after collision? Well, very simple. Their total momentum will be the same as it was before collision because they're in midair. There's no other force acting on them. Also, we assume they're not rotating in any way. So the total momentum will be the 800 kilogram meter per second momentum of the runner. Now we'll assume that the x direction is the direction of the runner's motion. So that'll be times the I vector. And the defender, we'll assume, is moving in the positive y direction. His momentum is going to be 540 kilogram meters per second times the j vector. Now again, the 800 kilogram meters per second comes from multiplying mass times velocity for the runner, and the 540 kilogram meter per second, the 90 kilograms multiplied by 6 meters per second. Again, momentum in the I direction, momentum in the j direction, so that mass times velocity is going to be just equal to that expression for the momentum. Now this is after collision, and I didn't do a lot of subscripting and so forth, but after collision, presumably, according to the conditions of the problem, there's no rotation, and the defender holds on to the runner. Runner doesn't shake free, so they move away as one mass. So it's their total mass times their common velocity is equal to the total momentum they had before collision. Now the momentum hasn't changed because there's no force on the two-mass system. Okay? The only force that's being exerted is the force between the two. Now that might be a considerable force, but it doesn't affect their common momentum. So there's no change in the momentum of the system. They're in midair. If they were in contact with the ground, there would likely be other forces involved. If you want to ignore air resistance, but they're not moving that fast. There's not that much air resistance. Okay. So there we have it. And then you can easily calculate the velocity from the fact that the mass of the two players, well, total mass is 190 kilograms, 190, so that the mass being this, the velocity is going to be this divided by the 190 kilograms, and I think that comes out within a tenth, 4.2 I plus 2.7 J meters per second. The speed is therefore the magnitude of this vector. Okay, there you have it. And that comes out, I think, pretty close to 5 meters per second. I didn't set it up to do that, but I think it's pretty darn close. You can work it out and see how close. And then the direction of motion is going to be the inverse tangent of 2.7 over 4.2, the inverse tangent of the y divided by the x component of this velocity, and that's going to be at 30 degrees. 30 degrees with the original direction, and that turns out to be 30 degrees relative to the positive x-axis measured in the counterclockwise direction as we, by default, measure the direction or indicate the direction of a vector.